My name is Rishabh. I'm gonna tell about the application of Rolle's theorem for determining the critical points in beam deflection curve. I am from CSE AIML branch. Abstract. This report explores the application of Rolle's theorem in identifying critical points in deflection curve of structural beams. Using classical Euler-Bernoulli beam theory, the study derives analytical expression, discusses mathematical foundation, validates results through numerical computation, and presents engineering implication. The report demonstrates how fundamental calculus principle ensures the existence of stationary points in deflection curves and how these are applied to determine the maximum deflection in beam under various loading conditions. The study expands towards FEM verification, experimental method, and advanced extensions. Introduction. Beams are essential structures members designed to carry transverse load. Determining beam deflection is crucial for ensuring serviceability and structural safety. Classical strengths of material provides analytical models to compute deflection, slope, bending moments, and shear forces, while engineering methods often focus on numerical or empirical outputs. Mathematical principles such as Rolle's theorem give fundamental guarantees about the nature of deflection of curves. Rolle's theorem ensures that if a beam deflection curve has equal value at 2 points, typically the supports, then at least one point within the interval must have zero slope. This stationary point corresponds to a local extremum, often representing maximum deflection. Understanding this connection is valuable in structural design, optimization, and failure analysis. Mathematical background. Rolle's theorem. Rolle's theorem is foundational result in single variable calculus. It states, let fx be continuous on closed interval a to b, differentiable on open interval a to b, and suppose that f of a is equal to f of b. Then there exists at least one c in open interval a to b such that f differential c is equal to 0. In engineering, deflection function of beams satisfy the continuity and differentiability condition. For a simply supported beam, the deflection at both supports are 0. Therefore, Rolle's theorem guarantees at least one critical point inside the beam span. This theorem gives an existence proof that does not require solving explicitly for the deflection of curve. However, engineering practice goes further by computing deflection functions and identifying exact location of maximum deflection. Beam theory, Euler-Bernoulli equation. The Euler-Bernoulli beam equation governs the deflection of slender beam subjected to transfer load En into fourth order differential equation of dy by dx is equal to q of function x, where E is Young's modulus, I is second moment of area, El is fluxual rigidity, Yx is deflection, Qx is equal to load distribution. For standard loading condition, integrating this fourth order differential equation yields formulas for bending moment, slope, and deflection. Boundary conditions determine the integration constant. In this report, we examine a simply supported beam under uniformly distributed load UDL, but extensions are provided later for point loads, varying loads, and continuous beams. Deflection curve of a simply supported beam with UDL. For a simply supported beam under uniform distributed load Q, the deflection formula derived from the beam theory is y of function x is equal to square bracket open q into x into bracket L cube minus 2Lx square plus x cube bracket close square bracket close divided by 24 EL. Properties of the function. It is continuous on closed interval 0 to L and differentiable on open interval 0 to L. y0 is equal to 0 and y in the function of L is equal to 0, satisfying the Rolle's theorem. The slope function is obtained by differentiation. The differentiation of the last slide function is equal to square bracket open q into bracket open L cube minus 6 into L into x square plus 4x cubed bracket close square bracket close divided by 24 into EL. To find critical point, we have to set the function with respect to x is equal to 0. Next step of solving the question is we have to solve critical points. We have to set the value of y differential of x is equal to 0. So we get L cube minus 6x square into L plus 4x cube is equal to 0. Factor out L cube. 1 minus 6 x square by L square plus 4 x cube by L cube is equal to 0. After that we have to assign a value to x by L as u. So we get 4u cube minus 6u square plus 1 is equal to 0. Solving the cubic equation yields u is equal to 0.5, that is x is equal to L by 2. Other roots may exist algebraically but lie outside the physical domain. Such the governing stationary point is at a mid-span. Second derivative test. To classify the stationary point, compute y double derivative of x. Y double derivative of x is equal to q into x bracket open x minus L bracket close by 2 into L into E. At x is equal to L by 2, y differential double differential L by 2 is less than 0. Thus the point corresponds to the maximum deflection. This matches engineering intuitions for a symmetrical loaded, simply supported beam. Let us consider a numerical example for better understanding of the concept. Consider L is equal to 6 meters, Q is equal to 5000 Newton meter, EL is equal to 1 into 10 power 7 1 Pascal. Maximum deflection occurs at x is equal to L by 2, which is 3 meters. Substituting value into deflection formula yields y in function of 3 is equal to, or which is approximately value of 8.44 millimeters. This value is within the normal serviceability limits for any steel and concrete beam designs. FEM verification. Finite element method FEM allow numerical verification. A beam model can be built using two-node Euler's-Bernoulli's beam element, uniform distributed load, simply supported boundary condition. FEM results typically show maximum deflection at midspan with negligible deviation from theoretical prediction. Such observations strengthen the validity of both the beam theory model and the application of Rolle's theorem. Experimental validation. Physical testing of beams can be conducted using steel or aluminium beam spacements, load frames applying distributed loads using sandbags or water tanks, dial gogs or LVDTs at 5-7 points along the span. Typical results. Maximum deflection is recorded at the mid-span. Experimental curve shows smooth deflection profile. Small deviation occurs due to shear, deformation material, imperfections and load application inaccuracies. Engineering application. Application of identifying critical points using Rolle's theorem. Quality control in structured testing, simplification in optimization of beam, identifying maximum stress zones, improving design of continuous beams, studying buckling modes in slender beams. Advanced extensions. The report can be extended to continuous beam, determine stationary points in multi-span system. Non-uniform loads, triangular loads, point loads and moment loads. Timoshenko beam theory include shear deformation effects, nonlinear large deflection theory, variable stiffness beams. So let us conclude our result. Conclusion. These reports demonstrate how Rolle's theorem guarantees the existence of critical point in beam deflection curves using analytical derivations and numerical example, FEM verification and experimental discussion. The study shows that maximum deflection consistently occurs at mid-span of symmetrical loaded, simply supported beams. The connection between pure mathematics and structural engineering strengths theoretical understanding and enhances engineering design capabilities. Thank you.